Lab 2, lines of charge. So we know that ordinary matter is electrically neutral, and rubbing, pulling apart, or touching another object can cause an object to acquire an excess charge. And so the purpose of this experiment was to determine the amount of charge on each tape necessary to float one above the other using the line charge model. And so first we divided the charge tape into a line of point charges, and then we computed the electric field of each piece, and then we added the electric field of all the pieces, which yielded the electric field of the charge tape. And this is known as the superposition principle. And so we found the charge of the tape to be 1.66497 times 10 to the negative 8th coulombs. So the lab procedure was the same as it was for lab 1, but the most important step was putting one U-tape above another to measure the floating distance. Some of the important tape dimensions that we found were that the mass was 0.0016 kilograms, the length was 0.2 meters, and the area was 0.003381 meters squared. So some of our underlying principles for our model is that the change in momentum over the change in time is equal to 0 on tape B, and so the net force on tape B is equal to 0. So that means the sum of the forces in the y direction is equal to 0. And using that, we can deduce that the magnitude of the gravitational force on tape B is equal to the magnitude of the electric force due to tape A. So some of our assumptions for our model is that each U-tape has the same net charge, which is evenly distributed along the length of the tape. And we are also ignoring air resistance on a moving object. And so here you can see one tape represented as a line of point charges. And I chose N to be 10. And this number represents the overall charge of the piece of tape, which is 1.66497 times 10 to the negative 8th coulombs. And this value represents the charge of one piece of the tape, which was 1.66497 times 10 to the negative 9 coulombs. And so for the analytical calculation of the net electric field, we treated the tape as a line of point charges, and we know that the charge distribution is uniform along the length of the tape from assumption number 1. And then this calculation is similar to the procedure for calculating the electric field of a uniformly charged thin rod. However, instead of one observation location, we have N, which represents the number of pieces of the tape. And so then we use these calculations to calculate the net electric field. For the coding procedure, we had first measured the separation distance at which tape B began to float above tape A, and we found this to be 0.0381 meters from lab 1, and then we placed the two strips of tape at this vertical distance in our computational model. And then we calculated dE, which is the contribution of each piece in the bottom tape to the net electric field of the top tape. And the total sum of the dE values gave us the net electric field, and then the electric field of one piece of top tape multiplied by the charge of one piece of top tape equals the electric force on one piece of top tape. And then adding the electric force on each piece of top tape yields the net electric force on the top tape. And so we use force equilibrium, which was described earlier using the gravitational force and the electric force to find the total amount of charge on the tape, which we found to be 1.66497 times 10 to the negative 8th coulombs. So this is the first slide of my code, and this is the second slide of my code. And here's my computational model, and it's important to note that the magnitude of the electric force is equal to the magnitude of the gravitational force. And the red spheres represent the top tape, and the blue spheres represent the bottom tape. So what if you had modeled each of your tapes as a single point charge like in the previous lab? Using the point charge model, we got the charge to be 1.59 times 10 to the negative 8th coulombs, and using the line charge model, we got the charge to be 1.66497 times 10 to the negative 8th coulombs. So why do these estimates differ, and which one is more likely to be closer to the real value, and why? So the value obtained from the line charge model is more accurate. Generally, the greater the number of point charges you apply to a given object, the higher the accuracy of the charge of the object. And this is because a larger number of point charges better resembles the individual point charges in an object. And so, in conclusion, ordinary objects can acquire excess charge if they are rubbed, pulled apart, or touch other objects. And the purpose of this lab was to determine the amount of charge on each tape necessary to float one above the other. This was done by calculating the contributions of each piece of the bottom tape to the net electric field of the top tape, which is known as DE, and then we could calculate the electric force on the top tape from those values. And so another important takeaway from this lab was seeing the higher accuracy of the line charge model as opposed to the point charge model.